Great. So thank you all for coming to my talk today. I'm going to be talking about Rheonics' newest innovation for the slurry industry. So the newest innovation is the self-cleaning sensors for automated continuous slurry viscosity and weight monitoring. To talk about this, I'm going to go through the background of what's being done for viscosity monitoring in the industry. We're going to talk about the motivation for why we developed this new technology. And we're going to go through the proof of concept, and we're going to look a little bit at some field trials to figure out what's going on in the future, or what's going on in the industry when we put our sensor in there. So, without further ado, we can talk about the background of viscosity and density in the slurry industry. Pretty much every foundry is going to be monitoring viscosity and density in some manner or another. These are to control for the shell adhesion and thickness. This is also to adjust for evaporation and your process control. This can indicate binder stability issues. It can tell you about contamination. Essentially a bunch of different things that are leading towards quality control of your shells. And since we always want to be building high quality shells, viscosity and density are monitored regularly every shift, if not every hour, depending on the facility. So the ways that are currently being done in industry at the moment is manual, and then we are in industry already working continuously in tank viscosity and density measurements. The manual measurements that we see are often cups for viscosity, sometimes offline measurements in laboratories, plate weight measurements, some various picnometers, and other density measurements. And then in the tanks, we've got an SRV and an SRD for viscosity with just the SRV, and viscosity and density with the SRD. So some of the challenges that arise in manual measurements is that they're intermittent. You're not continuously checking. And so if something has gone wrong in your slurry, you might not know for a couple of hours until your next cup measurement is done. The cup measurements also depend on the operator. In the best operator situations, they're very repeatable. However, there can be deviations between operators and deviations between timing on given days. If you've ever tried to work on your reflexes with a stopwatch, that can cause some difficulties. This also takes time for the operators, and they have to make sure that the cups are fully cleaned. Any deposits on the cups can affect your measurements, and you could accidentally over-dilute your slurry due to one errant or a couple errant cup measurements. Additionally, with manual measurements that are taken in the lab, there's some time delay before these can be put into your PLC system and could be adjusted for dosing or manual dosing of diluent. With inline measurements, we have been working to measure slurry viscosity in a lot of industries for the last almost 8 years. But in a few industries, we encounter a lot of questions about cleaning of the sensors. And this is because for some slurries, they adhere to the sensor even when it's fully submerged in the liquid, in the slurry. This doesn't happen at all, but we wanted to address that's quite a pain point for some to figure out exactly how often do we need to be cleaning it? Are we cleaning it often enough? Why are we cleaning some tanks more than others? So, of course, we want slurries to adhere to surfaces. So it does make sense that we're having this issue in this investment casting industry. But deposits that form on the sensor prevent us from getting good readings and can distort what we're seeing. So when we talk about the distortions that we're seeing, when we have deposits that form on a sensor, it will lead to a perceived increase in viscosity. These deposits, after about 3 days, this one should be cleaned, but after 4 days, we start seeing the deposits are formed and they're affecting the viscosity readings. And so observing these readings over time is required to help us find these cleaning frequencies. So if a customer came to us and asked us about how often we should be cleaning this sensor, we'd be saying every 3 days. But this is a huge hurdle towards using continuous measurements towards process control. And so we wanted to design something that would prevent deposits from forming on our sensors. With that motivation in mind, the desired outcomes that we have for this design is to give an uninterrupted reading, so we don't have to interrupt it for cleaning, We wanted to build in the cleaning mechanism that could do one of two things: either prevent the deposit from forming or remove deposits after it has formed on the sensor. This would reduce maintenance for operators, and it would also increase shell room operator trust, because we know that when deposits form on your sensor and you start getting a wild viscosity, that affects whether or not the plant operators are trusting the measurements that you're seeing. So all of these taken into account, was this even a possibility that we could do? And so we looked at a couple different options, one of which is to standardize the cleaning time. As I showed with the deposit graph earlier, you could come up with a cleaning time, but there's really too much variation between slurries. So even in a same facility, your slurries that are right next to each other might have different cleaning schedules, and you could clean them all at the lowest interval, but that would be time intensive. We've also looked into cleaning robots, and cleaning robots are a logical step for the investment casting industry, as there's so much of the industry that is using robots for dipping, for moving tanks around. So we checked into that, but there are some slurries that when you put a sensor in them, the deposit starts to form almost immediately. So the robots were just not going to be fast enough for the most challenging slurries. We looked into non-stick coatings, but by the nature of slurries having so many particles in them, we're dealing with abrasion at too fast of a rate for this non-stick coating to be relevant. So that left us with the self-cleaning option. And in order to develop a self-cleaning sensor, we set out the following list of requirements. We wanted it to be self-cleaning, and we also wanted it to prevent deposition. It needed to be compatible with our existing SRV and SRD technology, so the viscosity sensors that are already working in industry. We just wanted to add on something that could help us continue to use those in deposit-prone slurries. We wanted the cleaning mechanism to not interfere with the measurements, and of course, critically, to not interfere with tree dipping for the investment casting industry. To do this, we took inspiration from a dog shaking off after a bath. In the same way that the dog generates a flow field around him, and if you wanted to deposit something on him like a towel, you'd encounter some issues. A little bit of chaos would ensue with the towel and the dog. So with this flow field of liquid happening around the dog, we prevent deposits from forming at the surface, which allows us to come to our final design. Our design uses the SRD sensor, that's the viscosity and density sensor, with the exact same technology as before, but we build in a vibrator with a high amplitude and low frequency, and we've added a mount for adjustable height so you can stick it deeper into your slurries, and it's still able to move up and down if you'd like. We also have a fixed mount if that's preferred. So for this, we did some validation experiments in our, sorry, I walked away from the microphone. We did some validation experiments in our lab, and in order to do that, we did them on a small scale. We know that this is not exactly how it's done in industry, but we wanted to confirm it worked in our lab before we put our sensors out into the real world. So our early validation stuff was done with a kitchen mixer with a rotating bowl and a plow. This is different than what many of you might have in your kitchens. You might have a KitchenAid or a Kenwood, and that has a mixer that's mixing around in the middle. For our mixers, it's very similar. For our kitchen mixer, it's very similar to a slurry tank where the bowl is rotating and it's just a plow that's fixed at one point. To do this, we used a Ransom and Randolph suspended slurry. And we did this because we knew that this was a slurry that did tend to form deposits quickly, so we were able to test if we were able to slough off those same deposits or prevent those same deposits. The vibration is pneumatically actuated, which allows it to run in a dusty environment or an explosive environment without having while having an EX certification. And during these experiments, we kept the rotation speed of the drum constant and recorded the viscosity and density with our sensor in the normal manner without adjusting our sensor's technology, just adding on that vibration. We did 25 minutes without vibration and 25 minutes with vibration. And the results speak for themselves. When we have a vibration, when we have a period where the vibration is on, the readings are more stable, because the flow around the sensor is more consistent as it's flowing always the same way. When you have that dog shaking off, in theory, the dog is going back and forth, but the flow that's being generated by the vibration is happening in a repeatable manner, so we're getting consistent measurements. Now, this is not to say that the viscosity and density can't be measured when there's not vibration happening, but in some slurries, when the deposits are forming, this is a real concern. Another thing that we can see in this data is in the second period where the vibration is off, you can see that the viscosity measurements start to trend upwards. Let's see. And so when we turn the vibration back on, we can see that the measurements dropped back down almost immediately. This tells us that, one, we can have the vibration can operate continuously, which gives us these constant measurements, or if you don't want to have vibration operating continuously, the vibration can slough off deposits that have already formed. Also, during our experiments, we were able to come to the same measurement for density between on and off periods. So density and viscosity on and off periods. So if we had a consistent value, things might get wild when the vibration went off, but it would come back down to the same number. To confirm that the density was being measured accurately, we did a manual check in our laboratory to confirm that it's matching with some conventional measurements, density measurements in our lab. We, in the past couple of months, have been doing a variety of field trials of our sensors. And so we don't have data from the field trials from the site specifically, but we have some randomized data that has been shifted. So we have the real data that has matched these trends. In our field trials that we're running, we wanted to just put our sensor in the industry without adjusting anything the industry is doing. We wanted to make sure that if they're doing dilutions based on cups, everything is being run exactly the same as before. Just our sensor is being added, so we're having continuous measurements. With this, we can see what is happening without trying to adjust anything happening in the investment casting industry with our SlurrySense. We were doing this with a prime slurry in a couple locations, and we're doing them in prime slurries that were known to form deposits on our sensors in the past. At the time when I submitted these slides, we were at 5 months continuous operation for our longest trial, but we're up to about 7.5 months for our longest trial at this point. And so from the field trial, we got viscosity measurements and density measurements over the period of approximately 1 month. And during this time, no cleaning or inspection of the device was done. And so this was just to see what are we seeing after a whole month, what has changed, what's going on. During this, you can see that the viscosity has varied. However, when it's compared to what the investment casting industry, the partner was doing with their slurry, they were able to tell us that there's evaporation happening in certain events, and they were able to tell us, hey, at this time we did a dilution, and we were able to see that those dilution events lined up with when our viscosity dropped back down. It's also quite interesting to see that the density remained constant over the course of the month. Towards the end of the month, we zoomed in on some details of efflux cups measurements with the SRD that was running. And when we looked at those efflux cups measurements, we could see that when the evaporation was up, the efflux cups, when the evaporation was coming to the end, when they were coming back in on the Monday morning to start diluting their process, they did their efflux cup measurement and dosed diluent based on the efflux cup measurement, and the SRD viscosity reading followed the efflux cup reading and followed the dilution. And this is at near the end of the month. So we're talking 29 days into the month, so it has not been cleaned or inspected the entire month at this point. And when it was cleaned and inspected at the end of the month, they found there's nothing deposited on there. The cleaning is, just on the shaft of the device that's, near the surface level of the slurry. The sensor itself doesn't need any cleaning. The outlook for this device allows us to go back to those requirements that we addressed at the beginning. And those requirements that we had for our sensor was that it was going to be self-cleaning, and we wanted it to prevent the deposition from even forming. So self-cleaning, either prevent or slough off, we managed to have both features possible with our device. We wanted it to remain compatible with our existing sensor technology, and we didn't want the vibration feature of our CleanWave technology to interfere with the measurements. By installing it in field trials, we were able to confirm that it does not interfere with tree dipping. And with that, all of our requirements were met, and that tells us that we're able to look forward to the future of using our sensors in the shell room further in deposit-prone slurries. So this extends it to those deposit-prone slurries and can take a huge step forward towards Industry 4.0, where we're automating the whole system. This saves operator cleaning time, reduces reliance on inter-operator variability, and it allows operators to have an increased trust of the measurements that they're seeing from our device. So with that, I will take any questions, and also we have a booth downstairs, so you can ask questions now or also in the upcoming sessions in the exhibition hall.